iFour Technolab Private Limited, an ISO 9001-2015 certified and leading sustainable IT service provider. Presents tutorial of smart contract using Solidity. The purpose of this course is to give you complete understanding and hands-on experience with smart contracting using Solidity for blockchain technology. In Chapter 10, Structure of a Smart Contract, Part 2 covers an overview of structure of a smart contract and demystifies various structure of smart contract jargons. We are going to discuss the following topics: Enum Type, Struct Type, Events, Mapping, Error Handling, Interface and Abstract Contract. Enums can be used to create custom types with a finite set of constant values. Enum type can be used to create own set of values that can be assigned to a variable. It is one way to create a user-defined type in Solidity. They are explicitly convertible to and from all integer types, but implicit conversion is not allowed. The explicit conversion from integer checks at runtime that the value lies inside the range of the enum and causes a failing assert otherwise. Enums require at least one member, and its default value when declared is the first member. An example is taken to understand. Here, a contract named invoice is created which contains an enum of invoice status. Invoice status can now take any of the user-defined set of values. Invoice status can be waiting, approved or rejected. Approved or rejected. What is a struct? Structs are custom-defined types that can group several variables. Struct types can be used inside mappings and arrays, and they can itself contain mappings and arrays. A struct can't contain a member of its type, although the struct itself can be the value type of a mapping member, or it can contain a dynamically sized array of its type. This restriction is necessary, as the size of the struct has to be finite. Example. Here, in the example, invoice struct is taken with various variables into it. For example, id, from, to, subject, amount and status. We will see next how can we access these variables. As we already studied memory in the previous section, you can see in the example, this is how we can assign memory to the struct. Then, we can access any variable of the struct by using dot. For example, the ID variable of struct invoice can be accessed with this new invoice variable by writing a new invoice.id. It's a convenience interfaces with the EVM logging facilities. Solidity events give an abstraction on top of the EVM's logging functionality. Applications can subscribe and listen to these events through the RPC interface of an Ethereum client. Events are inheritable members of contracts. When you call them, they cause the arguments to be stored in the transactions log, a special data structure in the blockchain. The logs associated with the address of a contract are incorporated into the blockchain, and stay there as long as a block is accessible forever as of the Frontier and Homestead releases, but this might change with Serenity. The log and its event data are not accessible from within contracts, not even from the contract that created them. It is possible to request a simple payment verification (SPV) for logs, so if an external entity supplies a contract with such verification, it can check that the log exists inside the blockchain. You have to supply block headers because the contract can only see the last 256 block hashes. You can add the attribute index to up to 3 parameters, which adds them to a special data structure known as topics, instead of the data part of the log. If you use arrays, including string and bytes, as indexed arguments, its KECC K256 hash is stored as a topic instead. This is because a topic can only hold a single word, 32 bytes. All parameters without the indexed attribute are ABI encoded into the data part of the log. Topics allow you to search for events, for example when filtering a sequence of blocks for certain events. You can also filter events by the address of the contract that emitted the event. Mapping. Mapping types are declared as mapping underscore key type equals greater than underscore value type. The underscore key type can be any elementary type. This means it can be any of the built-in value types plus bytes and string. User-defined or complex types like contract types, enums, mappings, structs and an array type apart from bytes and string are not allowed. Underscore value type can be any type, including mappings. You can think of mappings as hash tables, which are virtually initialized such that every possible key exists and is mapped to a value whose byte representation is all zeros, a type's default value. The similarity ends there. The key data is not stored in a mapping, only its KECC256 hash is used to look up the value. Because of this, mappings do not have a length or a concept of a key or value being set. Concept of a key or value being set. Syntax. Mappings can only have a data location of storage and thus are allowed for state variables, as storage reference types in functions, or as parameters for library functions. They cannot be used as parameters or return parameters of contract functions that are publicly visible. Example. You can mark state variables of mapping type as public and Solidity creates a getter for you. The underscore key type becomes a parameter for the getter. If underscore value type is a value type or a struct, the getter returns underscore value type. If underscore value type is an array or a mapping, the getter has one parameter for each underscore key type, recursively. Error handling. What is assert and require? Solidity uses state-reverting exceptions to handle errors. Such an exception undoes all changes made to the state in the current call, and all its subcalls, and flags an error to the caller. When exceptions happen in a subcall, they bubble up. That is, exceptions are rethrown automatically. Exceptions to this rule are sent and the low-level functions call, delegate call and static call. They return false as their first return value in case of an exception instead of bubbling up. Assert and require. The convenience functions assert and require can be used to check for conditions and throw an exception if the condition is not met. The assert function should only be used to test for internal errors, and to check invariants. Properly functioning code should never reach a failing assert statement. If this happens, there is a bug in your contract which you should fix. Language analysis tools can evaluate your contract to identify the conditions and function calls that will reach a failing assert. An assert-style exception is generated in different situations, like if you access an array at a too large or negative index, if you divide or modulo by 0, if you shift by a negative amount, if you convert a value too big or negative into an enum type, if you call a zero-initialized variable of the internal function type, if you call assert with an argument that evaluates to false. The require function should be used to ensure valid conditions that cannot be detected until execution time. These conditions include inputs or contract state variables are met, or to validate return values from calls to external contracts. External contracts. A require style exception is generated in different situations, like calling requires an argument that evaluates to false. If you call a function via a message call but it does not finish properly, that is, it runs out of gas, has no matching function, or throws an exception itself, except when a low-level operation calls, send, delegate call, call code or static call is used. The low-level operations never throw exceptions but indicate failures by returning false. If you create a contract using the new keyword but the contract creation does not finish properly. If you perform an external function call targeting a contract that contains no code. If your contract receives Ether via a public function without a payable modifier, including the constructor and the fallback function. If your contract receives Ether via a public getter function. If a .transfer fails. You can optionally provide a message string for require, but not for assert. The following example shows how you can use require to check conditions on inputs and assert for internal error checking. Internally, Solidity performs a revert operation for a require style exception and executes an invalid operation to throw an assert style exception. In both cases, this causes the EVM to revert all changes made to the state. The reason for reverting is that there is no safe way to continue execution because an expected effect did not occur. Because we want to keep the atomicity of transactions, the safest action is to revert all changes and make the whole transaction, or at least call, without effect. Note: assert style exceptions consume more gas available to the call, while require style exceptions do not consume any gas starting from the Metropolis release. What is revert? The revert function is another way to trigger exceptions from within other code blocks to flag an error and revert the current call. The function takes an optional string message containing details about the error that is passed back to the caller. Example: the given example shows how to use an error string together with a revert and the equivalent required. The two syntax options are equivalent, it's developer preference which to use. What is an interface? Interfaces are similar to abstract contracts, but they cannot have any functions implemented. There are further restrictions. They cannot inherit other contracts or interfaces. All declared functions must be external. They cannot declare a constructor. They cannot declare state variables. Some of these restrictions might be lifted in the future. Interfaces are limited to what the contract ABI can represent, and the conversion between the ABI and an interface should be possible without any information loss. Interfaces are denoted by their keyword as illustrated in the example. Contracts can inherit interfaces as they would inherit other contracts. Abstracts. What are abstract contracts? Contracts are marked as abstract when at least one of their functions lacks an implementation, as in the following example. Note that the function declaration header is terminated by semicolon. Such contracts cannot be compiled, even if they contain implemented functions alongside non-implemented functions, but they can be used as base contracts. If a contract inherits from an abstract contract and does not implement all non-implemented functions by overriding, it will itself be abstract. Note that a function without implementation is different from a function type even though their syntax looks very similar. Abstract contracts decouple the definition of a contract from its implementation, providing better extensibility and self-documentation and facilitating patterns like the template method and removing code duplication. Abstract contracts are useful in the same way that defining methods in an interface is useful. It is a way for the designer of the abstract contract to say, any child of mine must implement this method. That's it in this video. Thank you for watching and stay tuned for our next video.